Okay, so we begin with a definition. Let G and this operation be a group. An element X in G is a conjugate, and that's the definition I wanted to introduce here. An element X in G is a conjugate to an element Y. So X in G is a conjugate to an element Y in G if and only if there is an element A in G such that A operation, and that's the group operation of course, X equals Y operation A. Okay, so that's the definition of a conjugate. Okay, so X is conjugate to Y. So in a group G an operation, an element X in G is a conjugate to an element Y. So X is a conjugate to an element Y in G, of course, if and only if there is this element A in G such that A operation X equals Y operation A. Okay. Alternatively, we can say that X is the conjugate of Y by A. Okay, that's another way to say it. Okay, we can say X is the conjugate of Y by A, or is a conjugate to Y. X is the conjugate to Y. Okay. So to this relation, a note here to this relation, we call it conjugacy. Okay, so we write it this way: X is conjugate of Y. Okay, this is the way we write it. X, it's a relation. Conjugation is a relation. Okay, X is conjugate of Y. Alternatively, or usually, we also express this saying, we also say X is conjugate of Y, and we define it as, this is another way. Okay, and usually this is very common. A operation X operation A inverse, I'm going to write inverse this way, equals Y. Okay, but if you look well, if you take this one, A operation X, so taking this one, A operation X equals Y operation A, A operation X equals Y operation A. If you take the product on the right, just group operations, so you can say A operation X operation A inverse, so we are taking the right inverse, y operation A, right inverse on both sides. Okay, so now A operation X operation inverse y operation, so this is the identity, A times the inverse is the identity. Okay, and the identity times y, y times the identity is y. Okay, so A operation X operation A inverse equals y. So that's why you can write it this way. Okay, as you can see, A operation X operation inverse equals y, so that's the same. Okay. Okay. Well, we can. There is a alternative definition for this. We can say X operation Y is defined as there is A in G, an element A in G, such that X operation A equals A operation Y. Okay? Or you can say X conjugate to Y is defined as there is an element A in G such that inverse X A equals Y. Okay, so A is in G and the inverse is in G too. Okay, or you can simply say A X operation inverse. Oh, I've seen this called also the transform of X by A. The transform of X by A. You can write this A inverse operation X operation A. Okay, the transform of X by A. Okay. Now, there is a theorem, I have to write it, okay, that says conjugacy of group elements, conjugacy of group elements is an equivalence relation. And this is very important because I was asked also about equivalence classes. So I was asked about conjugacy class. So this is very important because conjugacy is an equivalence relation, and we know that every equivalence relation gives rise to an equivalence classes. Okay, I'm going to repeat it. So conjugacy is an equivalence relation, and every equivalence relation give rise to equivalence classes. Okay. So now we have to prove this. I did not take any notes, but I think this is not hard, right? So conjugacy of group elements is an equivalence relation. So we have to prove that it is reflexive, right? Symmetric and transitive. This is not hard, okay? So let's go for reflexive. Okay, this is not hard. So we say for all X in G, we pick the identity of the group, for instance, operation X equals x operation g. So this implies that x is conjugacy of x. Okay, yes, so thus conjugacy of group elements is reflexive. That's not very hard. Okay, now we have to prove symmetry, right? We have to prove they are symmetric, right? Okay, so we take x, x is conjugate of y, right? So this means there is an A operation x equals y operation. Well, that's the very definition of conjugacy, right? Okay, now we can take these group operations. We take the yes, the right inverse. Okay, so right inverse on both sides. This is the identity, right? Okay, and this means that A operation x operation, so y times operation operation identity, it will be y. Okay, this is by group properties, right? This is easy. Okay, so since this is true, so y is also a conjugate of x. So x is a conjugate of y, and y is a conjugate of x. So that's this step by definition of conjugacy. Okay. Okay. So we take our obvious conclusion is thus conjugacy of group elements is symmetric. Okay. Okay, so checked for reflexivity, checked for symmetry, we now need transitivity. Okay, let me see. Okay. We are going to prove it is transitive. So x is conjugate of y, and y is conjugate of z. Okay, if x is conjugate of y, that's the definition of conjugacy, right? A1 times x, where times is this operation, equals y times A1. Now, I'm not taking only A, I'm taking A1 because I need another one for Z. Okay, and since y is conjugate of Z, A2, I have to distinguish these A's, A2 times y equals Z, right, times A2. So this is by definition of conjugacy. Okay? So so now we have x here, we can replace y there. It's really easy. You can do x null times a null times a1 times x equals a2 times y times a1 equal z equals z times a2 a1 times a1. Okay, you simply use group operations and you get to this conclusion. It's really easy. So this means that x is the conjugacy of z. Okay, x is conjugate of z, sorry. So if x is conjugate of y and y is conjugate of z, x is conjugate of z. Okay, so conclusion, thus conjugacy of group elements is transitive. Okay, so I think we can take the final. So all criteria are satisfied, and so conjugacy of group elements is shown to be equivalence relation. So conjugacy is an equivalence relation, and every equivalence relation gives rise to equivalence clauses. Okay, so we are going to check now that conjugacy, being an equivalence relation, it's going to partition the group G into equivalence classes. Okay? Okay, I'm going to pick again the definition. Okay, so G is a group. We pick two elements, A and B, in G. Okay, and now we know that they are conjugate, and A and B are conjugate. If there is an element, if there is a element G in G, such that G times A times G inverse equals B. Okay, so two elements, A, this is an A and B in G, they are called conjugate. A and B are called conjugate. If there is a G, an element G, and a group G, such that G times A times G inverse equals B. Okay? Very common also this way of this notation. So since conjugacy is an equivalence relation, it partitions G into equivalence classes. Very important, this. Okay, that's exactly what I was asked. Okay, and this is very important. Conjugacy and equivalence classes. Okay. What does that mean? Well, this means that every element of the group belongs precisely to one conjugacy class. Every element of the group belongs precisely to one conjugacy class. Okay, and we also say, and this is very important too, that classes, I'm going to note this way, CL, okay, class A and class B are equal if and only if A and B are conjugate, and otherwise they are disjoint and disjoint otherwise. Okay, so the equivalence class that contains A in G is class of A equals G times A times inverse, such that G is in G. Okay, and this is called, I have to write it, and is called the conjugacy class. It's called the conjugacy class. Conjugacy class of A. Conjugacy class of A. So the class number of G is the number of distinct non-equivalent conjugacy classes. Okay, that's the class. That's what we call class number of G. Class number of G is the number of distinct non-equivalent conjugacy classes. Okay. Now I think this is okay. The definition of what a conjugate is. When we say X is conjugate of Y, we know what it is. We proved that conjugacy is a equivalence relation, and we know that every equivalence relation gives rise to equivalence classes. So these equivalence classes, okay, the equivalence class are the conjugacy classes. Okay, so that is what a conjugacy class is. Okay. Okay, now I want to finish this. Since I've done a video with symmetry and all that sort of stuff, I want to give a more or less practical example of all this. So the equivalence class under the equivalence relation, so I'm going to give probably some, no, I'm going to give, not probably, I'm going to give examples of conjugacy conjugacy classes. Okay? But I want to use the examples of the previous video about the symmetry, the S3 and the dihedral groups and all that. So I'm going to take a group here. I think I've done on the other video, like the S3, okay, the symmetrical group, S3. So, what are the conjugacy classes for S3? One class is the identity, okay? So the identity is always okay. So what is the identity is 1, 2, 3, 1, 2, 3, written as in the previous video. Okay, this is the same as this. Okay. So this is one class. The other class would be, okay, I'm going to write in cycle notation here. I hope you guys are used to that. Otherwise, I can make a video for that. Okay, but for instance, 1, 2, 3. If 1 goes to 2, and 2 goes to 1, and 3 stays the same, okay. In cyclic notation, we say 1, 2. Okay, so this means 1 goes to 2, 2 goes to 1, 1 goes to 2, 2 goes to 1. So what about 3? 3 stays, 3 goes to 3. So you don't have to. Okay, these are the same notation. Not the same notation. These are the same. Okay, different notation. This is called cyclic notation. Okay, so I'm going to write here in cyclic notation. Okay, so all the 2 cycles, like 1, 2, 3, and 1, 2, 3. If I keep 2 and change 3 and 1, so this will be 1, 3, right? 1 goes to 3 and 3 goes to 1. And what is the last one? I'll keep 1, right? And this will be 2, 3, right? Yes, okay. All these 2 cycles are the same class. So I'm going to write it in cyclic notation. Okay, 1, 2, no commas here. Okay, 1, 2, 1, 3, and 2, 3. Okay, these are the 2 cycles, right? Okay, so this is a class, a conjugacy class. This is another class, the 2 cycles, and the other one will be the 3 cycles. Okay, so that will be 1, 2, 3, and 3 to 1, right? The 3 cycles. Okay, as you see, every element of S3 is in one of the classes. Okay, either it's in this one, or this one. Okay, and these are the conjugacy classes. Okay, so I hope you are used to this notation, but this video is not about that. Okay, I've also, the previous video I've done the D4, right? So what are the conjugacy classes for the D4? Okay. Let me see if I don't do the same mistake. Someone told me I made a mistake on the previous video. I'll go back and check that in a minute. Okay, so the conjugacy classes for D4 will be the identity, of course, that's one. The other one will be, if we rotate 1, 2, 3, 4, if we rotate 180 degrees, so if 1 goes to 3 and 3 goes to 1, right? So 1, 3, 3, 1. And the other 180 degrees rotation is 2 goes to 4 and 4 goes to 2, right? So 2, 4. Cyclic notation. Okay? So this is 180 degree rotation, right? Okay. Okay, and so this one is one class, this one is another class. The other one will be the edge reflections. Okay, so that will be 1, 4, 2, 3, right? So be careful with this cyclic notation. 1 goes to 4, 4 goes to 1, 2 goes to 3, 3 goes to 2. Okay, and 1, 2. So these are the edge reflections, right? 1, 2, 3, 4. Okay, these are the edge reflections. 1 class, 2 class, 3. Now the vertex ones, 1, 3, and 2, 4, right? 1, 3, and 2, 4, right? Yes. Okay. This is the vertex reflections, and the last one will be the 90-degree rotations. Okay, I think that's the one where I have some mistake. I think 1, 2, 3, 4, that's yes, and 4, 3, 2, 1, that's the 90 degrees rotations, right? All these rotations. Okay, I think we could write this as, let me see if I can, we could write this as we could write this in matrices, right? So the identity in matrices, the identity is 1, 0, 0, 1, right? Okay. Okay. You can write this as matrices 1, 0, 0, 1, and it's a good exercise. So that the sect of this matrix. The other one is what? The 180-degree rotation. Okay, that would be what? That would be -1, 0, 0, -1, right? Okay, that's 180-degree rotation. Now the edge reflections would be -1, 0, 0, 1 and 1, 0, 0, -1, right? Okay, that's the edge rotations. What about the vertex reflections? Would be 0, 1, no? 1, 0, right, yes. And the other one, this with a minus, yes. Okay, these are the vertex reflections. And what's the last one? 90-degree rotations. 0, 1, -1, 0. And the last one is 0, -1, 1, 0. These are clearly the 90-degree rotations. Okay, you can try for instance, the alternative group A4. Try for that. Okay, A4. If you can't make it, just let me know. Okay.